Okay, let's pick this up with a few more examples. I went to the next tab here, infant crawling. So the data here looks at the month an infant was born in and the average number of weeks that the babies born in, for example, January learned to crawl. So if you read this, 32 babies born in January took them an average of 29.84 weeks to learn how to crawl, with a standard deviation of 7.08 weeks, which we talked about as a measure of how spread out they are. So not each of these babies was exactly the same. They were spread out quite a bit, but this was the average. We also have the average monthly temperature 6 months after birth. The hypothesis is here that babies who are trying to crawl in colder months, their parents have them more bundled up, so it takes them longer to learn to crawl. And we can see if the data might back this up. So once again, to make the scatter plot easy, I took my temperature and copied and pasted that over here, my average crawling age over here. Once again, we're trying to see if temperature predicts average crawling age, so we want average crawling age to be the y. So we scroll over and we see, oh yeah, there is kind of a negative relationship here. There is kind of a downward trend. But then we also have this one dot here, which looks way lower than the trend. So we're kind of like, what is that? And the interesting thing about this one is this isn't just one baby. This is the average of, that was May, so it's 27 babies had this weirdly low average. So we don't really know why that is. We don't have the full data, but we just need to talk about this. A moderate negative correlation between temperature and average crawling age. There's a possible outlier for May, which has a lower average crawling age than the pattern would indicate. Calculate the correlation coefficient. Again, just using this equals correl command, select the values, comma, select the other values. And then I just made another note here. It's a semi-influential outlier that if we did the same calculation without May, we'd get a different number. But let's move on to alcohol and tobacco. So here we have the average weekly household spending in British pounds on tobacco products and alcoholic beverages for each of the 11 regions of Great Britain. So this is just the average spending on alcohol and tobacco in North Yorkshire, Northeast, Midlands, all these. If you know your Great British geography, this probably makes more sense. I don't know it super well, but we have data on it anyway. So if you look at this, we make the scatter plot. We're not really trying to predict one or the other here, so it doesn't really matter which one is X and Y. So I just put them in the order they are with tobacco on the Y-axis. So you can see there is kind of a relationship here in that it's going up. So I'd say a moderate positive correlation between spending on alcohol and tobacco. But this is Northern Ireland, this last point here, which is quite an outlier because it's very low in the alcohol spending, but it is the highest in the tobacco spending. So what's going on with that? So when we calculate our correlation coefficient, we can see we get a value of 0.2236, which is extremely low. It indicates quite a weak correlation, but that's driven a lot by this outlier. If we do the same calculation without the outlier, and you can see how I did that, I just did the same command, I just didn't drag it all the way down. Of course, Excel gives me a little green triangle here indicating, did you mean to do that? Then I get 0.7843. So that's another thing about correlation, just like the mean or the standard deviation. It's very sensitive to outliers. So one outlier can really throw it off. You do the same scatter plot without it. You can see this line I put in, just again with the plus sign here, and add a trend line, really fits the data a lot better. Let's also look at, let's skip this one and go to car mileage. So here we have data on some classic cars. I don't know the exact year, but there are 82 cars here. You can guess this data is a little old because you have things like the Subaru Justy, the Geo Metro, and such. But we have the cubic feet of cab space, horsepower, miles per gallon, top speed, and the vehicle weight that they somehow, for some reason, put in hundreds of pounds. So the question we want to answer is, what's the relationship between horsepower and fuel economy? So we want to predict fuel economy in terms of miles per gallon based on the horsepower. You probably expect that cars with lower horsepower get better gas mileage. So if you look at the scatter plot, you can see it backs that up quite well. Cars with higher horsepower generally have fewer miles per gallon. On the low end, this car was extremely high, 65 miles per gallon, but 49 horsepower. Not a lot of people buying that these days. So you'd say there's a strong negative association. You don't say correlation because this is not a straight line relationship. It is clearly curved. So if you want to be more specific, miles per gallon decreases rapidly at first and then more slowly. Does it really level off? Well, we don't know. There are so few dots at the high end here. But the correlation coefficient can be misleading because this is a curved relationship. And R, your correlation coefficient, only measures the strength of the linear relationship. So if we do calculate it, it's almost negative 0.8. So if you just looked at this number without looking at the scatter plot, you would be like, wait, that looks like a pretty strong correlation. But then you look at the scatter plot and you're like, nope, nope, it's actually a strong association. So that's why you always need the scatter plot and the correlation coefficient to really get the full picture of what's going on. Scatter plot also helps you spot outliers. This one doesn't look like it really has any, but just in general, you might run into those quite a bit.